What would happen if all of Earth's continents merged into a single landmass? This is not a hypothesis. Around 300 million years ago, it actually happened. A colossal stretch of land large enough to alter the climate of an entire planet witnessed the greatest mass extinction in history and paved the way for the rise of the dinosaurs. But the secret of the Age of Dinosaurs did not begin with their evolution. It began with Pangea, the supercontinent that shaped the fate of life on Earth. Pangea is often described as the largest supercontinent in Earth's history. But when nearly all of Earth's land masses merged into a single landmass, Pangea stretched across more than 130 million square kilometers. It was a continent so vast that the distance from the coastline to its interior could reach thousands of kilometers. Today, much of Earth's climate is regulated by the oceans. Seawater absorbs heat during the day, releases it at night, and transports energy around the planet through ocean currents. But in the heart of Pangea, the cooling and moderating influence of the oceans nearly disappeared. The result was a phenomenon geologists refer to as a supercontinental arid zone. Paleoclimate studies using modern computer models suggest that many regions within central Pangea may have experienced summer temperatures exceeding 40 degrees Celsius and at times even higher. Differences between daytime and nighttime temperatures, as well as seasonal temperature swings, were far greater than those experienced across most regions of Earth today. Remarkably, evidence of that harsh world still exists. Across modern continents, such as North America, Africa, and Europe, geologists have discovered vast layers of red sandstone whose ages correspond to the time of Pangea. These rock formations, commonly known as red beds, formed under intensely oxidizing conditions and prolonged hot, arid climates. During the summer, the immense landmass heated rapidly, causing air to rise violently and draw moisture inland from the ancient Panthalassa Ocean and the Tethys Sea. It was a world of extremes, a world where life had to adapt not only to heat or cold, but also to constant climatic instability. If Pangea was so harsh, how did life survive? It was like a gigantic evolutionary laboratory. Every drought, every period of extreme heat, and every climatic fluctuation continuously filtered life on a planetary scale. Yet the frightening reality is that none of these challenges would become the greatest threat. A single event would kill the majority of life on Earth, erase nearly entire ecosystems, and push the planet to the brink of becoming a dead world. This was the moment when our planet came closer to total biological collapse than at any other time in known history. Paleontologists call it the Permian-Triassic extinction event, but many know it by a far more chilling name, the Great Dying. Fossil evidence shows that roughly 90% of all species on Earth were wiped out. In the oceans, as many as 96% of marine species disappeared. On land, approximately 70% of vertebrate animals became extinct. This was the collapse of nearly the entire web of life. What could have caused a catastrophe on such a scale? Beneath the frozen forests of northern Russia lie the remnants of one of the most terrifying geological events ever recorded. Scientists call it the Siberian Traps. Around 252 million years ago, this region began erupting on a scale almost impossible to imagine. Lava did not erupt for merely years or centuries like ordinary volcanic events. The total volume of lava released may have exceeded 3 million cubic kilometers. Modern climate models suggest that Earth's average temperature may have risen by 8 to 10 degrees Celsius. The oceans were among the first systems to feel the impact. As seawater warmed, its ability to hold oxygen declined. A chain reaction was set into motion. Coral reefs disappeared. Food webs collapsed. Global warming, oxygen depletion, ocean acidification, toxic gases, collapsing food chains. There was no place that was truly safe. The fossil record shows that after this event, Earth entered a strange new phase. Among them was one branch of life that, at the time, no one could have imagined would go on to dominate the planet for more than 160 million years. They were the first dinosaurs. Many groups of ancient reptiles were attempting to take advantage of the ecological niches left vacant after the mass extinction. Some were predators with crocodile-like forms. Others were large herbivores. The archosaurs, the common ancestors of crocodiles and dinosaurs, began diversifying at a remarkable pace. Surprisingly, the first dinosaurs were not particularly impressive. The oldest known fossils, such as Eoraptor from Argentina, date to approximately 231 million years ago. This animal measured only about 1 meter in length and weighed less than 10 kilograms. An average adult today could easily weigh 7 to 8 times more than it did. One of its close relatives was Herrerasaurus, which also lived in what was once ancient South America. Although it was a predator, its body length was only about 4 to 6 meters, far smaller than the giants that would appear later. In Brazil, Styracosaurus also represented one of the earliest generations of dinosaurs, with a slender body and the ability to move quickly. In reality, throughout most of the Triassic period, dinosaurs accounted for only a small fraction of terrestrial animal communities. Numerous fossil studies indicate that in some early ecosystems, they made up less than 10% of large vertebrate populations. What allowed them to survive? Anatomical analyses suggest that early dinosaurs possessed an upright leg posture beneath the body, rather than a sprawling stance like many ancient reptiles. As they moved, energy was used more efficiently, allowing them to run farther and faster. The respiratory systems of dinosaur ancestors may also have evolved to be more efficient than those of many contemporary species. Some evidence from bone structures suggests that primitive air sacs, a feature that would later become highly developed in birds, may already have begun to emerge within their evolutionary lineage. Some ancient relatives of crocodiles were larger, more numerous, and appeared far more successful. They dominated many terrestrial ecosystems, from riverbanks to vast plains. As environments continued to change, many formerly dominant groups began to struggle. Meanwhile, small dinosaur populations quietly expanded their range. They appeared across an increasing number of regions throughout the supercontinent of Pangea. From the ancient valleys of Argentina to lands that are now part of Brazil, and eventually across Africa and many other regions of the supercontinent. How could a group of animals that initially appeared in only a few small regions eventually spread across an entire planet? An animal could begin its journey in a region corresponding to present-day Argentina, and over many generations, its descendants could spread into lands that would later become Africa, Europe, or North America without crossing a single ocean. The oldest known dinosaur fossils, discovered in the Ixigualasto Formation of Argentina, date to approximately 231 million years ago. Yet only a few million years later, closely related fossils appeared in Zimbabwe, in southern Africa. Similar traces have also been found in North America, Greenland, and many regions of ancient Europe. Phylogenetic studies suggest that within just 15 to 20 million years of their appearance, multiple early dinosaur lineages had already spread across most of Pangea's land area. On a geological timescale, that was almost an explosion. Why does this matter? Because a wide geographic distribution means a greater chance of survival. A population confined to a single region can be easily wiped out by local environmental change. But when a group of organisms is spread across tens of millions of square kilometers, the risk of extinction decreases dramatically. Pangea unintentionally created a planetary-scale biological insurance system for animal groups capable of expanding their territory. It also encouraged genetic exchange. As populations regularly came into contact with one another, genetic material was continuously mixed. Beneficial mutations that emerged in one region could spread into others. Pangea did not merely allow dinosaurs to move. While many other animal groups remained restricted to specific ecological zones, dinosaurs gradually became the travelers of the supercontinent. They adapted to open woodlands, arid plains, river valleys, and even semi-desert environments. Each new environment became a new evolutionary laboratory. And as dinosaurs continued expanding across that immense supercontinent, they were doing more than simply claiming new territory. They were leaving behind clues that would survive for hundreds of millions of years. Fossils, footprints, plants, and animals appeared on continents that today are separated by vast oceans. It all began with what seemed like a remarkably simple observation. While studying a world map, Alfred Wegener, the German scientist of the early 20th century, noticed that the eastern coastline of South America and the western coastline of Africa fit together with astonishing precision. Yet the shape of the coastlines was only a clue, not proof. The first real evidence came from fossils. An ancient reptile known as Mesosaurus attracted particular attention from scientists. Mesosaurus lived approximately 280 million years ago, measured about 1 meter in length, and spent most of its life in freshwater environments. The strange fact was that fossils of this animal were discovered in eastern South America and southern Africa. Today, these two regions are separated by the Atlantic Ocean, which stretches thousands of kilometers across. A freshwater reptile would have had virtually no chance of crossing such a vast ocean. The most reasonable explanation is that South America and Africa were still connected when Mesosaurus was alive. As researchers looked deeper, paleontologists discovered more examples of the same pattern. Fossils of Cynognathus, a mammal-like predator that lived during the early Triassic period, were found in both South America and Africa. Fossils of Lystrosaurus, a herbivorous animal with a distinctive horn-covered beak, appeared in South Africa, India, and even Antarctica. These were all land-dwelling animals with no ability to cross oceans, yet their remains appeared on continents now separated by thousands of kilometers. Each fossil was like a message from the distant past, and every one of them told the same story. The continents had once stood side by side. Animals were not the only witnesses. Plants also left behind critical evidence. One of the most important examples was Glossopteris, a seed-bearing plant with long tongue-shaped leaves that flourished during the Permian period. Fossils of Glossopteris have been discovered in South America, Africa, India, Australia, and Antarctica. Viewed through the lens of modern geography, this distribution is almost impossible to explain. But when scientists reconstructed the continents according to the structure of Pangea, the fossil-bearing regions connected perfectly. Suddenly, a clear pattern emerged from data that had once seemed unrelated, yet fossil evidence was not the most convincing line of proof. Geology provided an even stronger layer of evidence. While studying mountain ranges on opposite sides of the Atlantic Ocean, scientists noticed similarities that were too remarkable to ignore. The Appalachian Mountains of eastern North America share nearly identical geological ages, mineral compositions, and tectonic structures with the Caledonian mountain ranges of Scotland, Ireland, and Scandinavia. Farther south, rock formations within Morocco's Anti-Atlas Mountains display characteristics strikingly similar to ancient mountain systems in North America. Geophysicists began studying ancient magnetism preserved within volcanic rocks. As lava cools, iron-bearing minerals align themselves with Earth's magnetic field at that moment in time. The results revealed that today's continents once occupied completely different locations and could be reassembled into a single unified landmass. Pangea is not a hypothesis built on speculation. It was a real geological entity that once existed. Fossils tell part of the story. Mountain ranges tell another. Ancient magnetic fields provide the missing details. And once the existence of Pangea was no longer a mystery, an even greater question began to emerge. What happens when nearly all of a planet's land is concentrated into a single massive continent? After proving that Pangea truly existed, if nearly all of Earth's land had once been merged into a single colossal landmass, how did that affect evolution? As scientists began investigating the climate of this supercontinent in greater depth, they realized that Pangea was not merely a place where dinosaurs lived. It was also a natural selection system operating on a planetary scale. In many cases, the most successful species were those that adapted most rapidly to change. Geological studies of ancient lake sediments from North America, Europe, and North Africa reveal that rainfall during the Triassic period fluctuated dramatically in recurring cycles. Many regions experienced prolonged droughts before suddenly shifting into wetter conditions. Viewed from space, Pangea resembled a gigantic climate machine, constantly rewriting the rules of survival. Areas that were once fertile could become barren within only a few thousand years. The fossil record shows that many animal groups that dominated the early Triassic thrived in relatively stable environments. But as environmental conditions became increasingly unpredictable, their advantages began to fade. This was where dinosaurs started to make a difference. For most of the Triassic period, dinosaurs were not yet the dominant group. However, numerous studies of anatomy and growth rates suggest that they possessed characteristics exceptionally well suited to a constantly changing world. Their upright limb posture beneath the body allowed them to move efficiently across long distances. Some isotope studies of fossils even suggest that many early dinosaurs may have remained active under a wider range of climatic conditions. Species that failed to adapt quickly enough gradually disappeared from the fossil record. Those that adapted more successfully survived and passed their advantageous traits on to the next generation. Today, many paleontologists believe this was one of the key reasons dinosaurs became increasingly widespread throughout the late Triassic. Every time the climate changed, every time ecosystems were reorganized, dinosaurs repeatedly appeared among the groups that survived. To rise to absolute dominance, they would need one more opportunity. Around 201 million years ago, dinosaurs had already existed for tens of millions of years. They had proven their ability to adapt within the ever-changing world of Pangea, yet they were still not the dominant rulers of the planet. In fact, most ecosystems at the time were still controlled by ancient relatives of crocodiles, non-dinosaur archosaurs, and many other groups of large reptiles. Then a massive geological event unfolded. Today, it is known as the Triassic-Jurassic extinction event. Fossil studies indicate that approximately 50% of all species on Earth disappeared during this period. Remarkably, the cause lay deep beneath the surface of Pangea itself. As the supercontinent began experiencing its first major tectonic stresses, enormous fractures opened across Earth's crust in many regions. Through these fissures, magma surged continuously for hundreds of thousands of years. The result was the formation of one of the largest magmatic provinces in planetary history, known as the Central Atlantic Magmatic Province, or CAMP. This immense geological structure stretched across regions that today belong to North America, South America, West Africa, and Europe. The scale of CAMP is almost beyond imagination. Each eruptive episode released vast quantities of carbon dioxide into the atmosphere. Ancient climate models suggest that atmospheric CO2 concentrations may have risen above 2,000 parts per million, many times higher than pre-industrial levels on modern Earth. What is astonishing is that the fossil record shows many archosaur groups that had once thrived throughout the Triassic nearly vanished completely. Rauisuchians, apex predators reaching lengths of 6 or even 7 meters, disappeared from history. Numerous groups of large herbivores also failed to survive this period. From being a group that occupied only a small portion of late Triassic ecosystems, they became the most widespread large vertebrates across vast regions of Pangea. Within only a few million years, the world had changed completely. What allowed them to overcome this catastrophe remains an active area of scientific research. Many scientists believe that their earlier evolutionary history had already prepared them for it. Tens of millions of years spent living in unstable environments may have given dinosaurs a greater ability to withstand large-scale climatic change. Efficient locomotion, rapid growth rates, and the capacity to exploit a wide variety of habitats may have provided the decisive advantages as their competitors gradually disappeared. This is one of the great paradoxes in the history of life. A crisis once regarded as a disaster became the greatest opportunity dinosaurs would ever receive. Without camp, without the Triassic-Jurassic extinction event, dinosaurs might have remained only a moderately successful branch in the story of evolution. But when the planet entered a period of chaos, they were among the few groups capable of enduring it. By the beginning of the Jurassic period, for the first time in Earth's history, dinosaurs truly held dominion over terrestrial ecosystems. Yet the story was far from over. While dinosaurs were expanding their influence across the world, another transformation was quietly unfolding beneath their feet. And when Pangea began tearing itself apart, it would open the next chapter in the greatest evolutionary revolution of dinosaur history. After surviving the Triassic-Jurassic extinction event and securing dominance over life on land, dinosaurs seemed to be enjoying the greatest advantage history had ever granted them. If we could look through the tens of kilometers of rock beneath Pangea around 175 million years ago, we would see that the molten mantle below was far from motionless. Heat from Earth's core generated slow-moving currents, advancing only a few centimeters per year. Yet when operating over tens of millions of years, they possessed the power to move entire continents. At first, the changes were almost impossible to notice. Small fractures gradually widened over millions of years. However, like a gigantic sheet of glass subjected to continuous pressure, there came a point when rupture became unavoidable. Geologists call this process rifting, the stretching and separation of continental crust. As the crust is pulled apart, it becomes thinner and begins to subside. Magma from the mantle rises to fill the newly formed fractures. Vast rift valleys emerge, some hundreds of kilometers wide and thousands of kilometers long. These were the first cracks signaling that Pangea was beginning to divide itself apart. Remarkably, evidence of this process still exists today. The eastern coastline of North America and the northwestern coastline of Africa are locations that once lay along the same ancient fault system. At first, these were merely narrow seas similar to today's Red Sea. But over time, new ocean floor continuously formed through the process of seafloor spreading. The average rate was only about 2 to 5 centimeters per year, roughly the speed at which human fingernails grow. It sounds almost meaningless, yet over 10 million years, that distance can become hundreds of kilometers. This was a turning point in planetary history. For hundreds of millions of years, Pangea had functioned as a unified world. Now, for the first time since the supercontinent formed, geographic barriers were beginning to appear. As populations became separated by mountains, seas, or increasingly vast distances, the flow of genetic exchange began to decline. Because Pangea was creating a new world, and it was the breakup of Pangea that would pave the way for the most spectacular explosion of biodiversity in the entire history of the Age of Dinosaurs. Around 175 million years ago, Pangea began to break apart. The breakup of Pangea transformed the entire planet into a network of gigantic evolutionary laboratories. The result was extraordinary. Over the next 100 million years, dinosaurs evolved into hundreds of species with dramatically different forms and sizes. In North America and Africa, gigantic sauropods flourished. One of the most famous representatives was Diplodocus, a creature approximately 27 meters long. With a neck and tail resembling two enormous biological cranes. It may have weighed between 12 and 16 tons. Yet it maintains such a massive body through an efficient respiratory system similar to that of modern birds. Meanwhile, predators also began to diversify. Allosaurus emerged during the late Jurassic, reaching lengths of approximately 8 to 10 meters. It became one of the dominant predators of North American ecosystems. Biomechanical studies suggest that its skull was designed to withstand repeated bites against large prey, unlike the crushing bite force strategy later employed by Tyrannosaurus. In Gondwana, the southern portion of the former Pangea distinct evolutionary lineages began to emerge. This was where the titanosaurs evolved. Some species, such as Argentinosaurus, may have exceeded 30 meters in length and reached masses of 60 to 70 tons. This was where the titanosaurs evolved. Some species, such as Argentinosaurus, may have exceeded 30 meters in length and reached masses of 60 to 70 tons. They rank among the largest land animals ever to exist in Earth's history. Farther north, on the continents forming from Laurasia, a completely different evolutionary path unfolded. Armored dinosaurs such as Ankylosaurus developed dense bony protection across their backs. Some individuals possessed tail clubs weighing dozens of kilograms, capable of generating impacts powerful enough to break an opponent's bones. At the same time, the ceratopsians, the horned dinosaurs, began diversifying rapidly. Their enormous horns and neck frills were not used solely for defense. Modern fossil research suggests they also played important roles in social communication, species recognition, and reproductive competition. If Pangea had never broken apart, the dinosaur world might have been far less diverse. The gigantic titanosaurs of South America might never have appeared. The bizarre horned ceratopsians of North America might never have evolved. Tyrannosaurus itself may never have followed the evolutionary path we know today. This was the culmination of more than 100 million years of continuous evolution. A biological explosion whose deepest origins began on the day the supercontinent Pangea started tearing itself apart. Pangea was not only the largest supercontinent ever to exist, it was the single most influential platform in shaping the history of life on Earth. By merging all land masses into one, it erased natural boundaries and created unprecedented climatic and ecological upheavals, allowing early dinosaurs to spread across vast territories and ultimately dominate the planet after the end Permian mass extinction. Looking back on that journey, the dominance of dinosaurs was not a coincidence of fate, but the inevitable outcome of the planet's largest scale transformations. The collapse of Pangea brought one era to an end, but it also left behind powerful evidence of a profound truth. On an Earth that is constantly changing, even the greatest biological empires are only brief chapters, written by geological processes unfolding over billions of years. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.